Welcome back to the deep dive. Today, we are undertaking a pretty monumental task. We're cracking open Chapter 17, Space-Time, from the Feynman Lectures on Physics, Vol.1.
Yeah, this is foundational stuff.
And it's really not just about, how fast things go. It's about fundamentally changing how we define existence itself. Position, time, the basics.
That's exactly right. For centuries, physics treated space, the stage and time, the clock, as completely separate, absolute, unchanging things.
Right. Universal for everyone.
Exactly. But this chapter just forces us, really, to abandon that intuition. Our source material, Feynman, argues that when you bring relativity into the picture, space and time become inseparable.
So the things we thought were fixed, like where something is or when something happens,
they turn out to be relative, fundamentally relative to the observer.
So our mission for you, the listener, is to try and grasp the geometry of this new reality. We want to understand why space and time merge.
And how that merger dictates the rules of causality, basically. What events can influence other events, what we can influence.
And also how it forces us to redefine core physical laws, like conservation of momentum and energy. It's not quite what we learned in intro physics anymore.
It really isn't. We're diving deep into the actual geometry of reality itself and realizing, well, that reality is four-dimensional.
Okay, let's unpack this four-dimensional geometry then. Starting with maybe the weirdest part, the idea that measuring position and measuring time are somehow mixed up.
Yeah, that's the heart of special relativity, isn't it? Your measurements of space and time fundamentally depend on your velocity relative to whatever it is you're measuring.
So if I'm in my lab, standing still.
Right, and you measure an event where and when it happens.
Okay.
And then let's say you are speeding past my lab in a rocket, and you measure the same event.
My numbers for position and time will be different from yours.
They will be different. And it's not just measurement error, it's fundamental.
And the math that tells us how they differ, that's the Lorentz transformation we hear so much about.
That's the one. It's essentially the rule book for how coordinates change, how they mix in this four-dimensional space-time.
So how does it work conceptually?
Well, if you're moving at a constant velocity, relative to me, your new measured position, let's call it $6,
right,
doesn't just depend on my $6. It also depends on my time measurement.
Okay, so space depends on time.
And crucially, the reverse is also true. Your new time measurement doesn't just depend on it also depends on my position measurement, $6.
Wow, so space and time coordinates are just tangled together.
Fundamentally interwoven, yes.
Feynman uses this really helpful analogy, doesn't he?
Yeah.
About rotation in normal space.
He does, and it's quite clever. Think about looking at a box in normal 3D space. You measure its width and its depth.
Right.
Now, if you tilt your head or rotate the box, what you now perceive as its width isn't purely the original width anymore, is it?
No, it's like a combination of the original width and depth.
Yeah.
Because I changed my viewing angle.
Exactly. Rotation mixes the spatial coordinates, say x and y. The Lorentz transformation does something analogous, but it's wilder.
How so?
Just as rotation mixes two space dimensions, relative velocity moving in space-time mixes a space dimension like x and the time dimension, t.
Huh. So time becomes almost like another direction in this four-dimensional space.
In a mathematical sense, yes. Your time measurement becomes a component related to your motion through space-time. It's part of the angle you're viewing things from, metaphorically speaking.
So the whole idea of an absolute position or an absolute time, that just goes out the window with relativity.
It belongs to classical physics. Now we see measurements of space and time as just two different aspects or projections of the same underlying four-dimensional reality.
Viewed from a particular velocity.
Precisely. And they are fused into this single entity we call space-time.
And this perspective is essential, especially when things move really fast, near light speed.
Absolutely necessary. The coordinates aren't independent anymore. And that fusion, that interconnectedness, dictates what is constant, what doesn't change. Which brings us to the geometry, the actual shape of this new space.
Right. If space-time is this new blended reality, how do we measure distance in it? In ordinary 3D space, distance squared is just 6 pi$ plus y2 plus z22, simple addition.
But we already know space-time isn't ordinary Euclidean space.
So the formula must be different.
It is, and this is critical. In space-time, The quantity that remains invariant, the objective measurement that all observers agree on, no matter their velocity, is called the space-time interval.
Okay, the interval. That's the real distance.
That's the analog of distance in this four-dimensional reality. It's what doesn't change when you apply the Lorentz transformation.
And how is it defined? This is where it gets weird, right?
It is. When we calculate the interval squared between two events, we take the time difference squared, multiplied by 2 neighbors 2, the speed of light squared, and then we subtract the squares of the spatial separations. 6 by the c, 652, 62,002.
Subtract, not add.
Yes. Those minus signs in front of the space components, c2t2 by 2y2, z2 to 2, are the whole key. They tell us the geometry is fundamentally non-Euclidean. It behaves differently from the space we're used to.
Why is subtraction such a big deal conceptually? What does it do?
Well, think about regular distance squared. 6 by dollars plus y2 plus z2.
Yeah.
It's always positive, right? Or 0 if the points are the same.
Sure.
But because of the subtraction in the space-time interval, the result squared can be positive, it can be negative, or it can be 0.
Positive, negative, or 0. Okay, what does that mean?
If the interval squared is positive, we call the separation time-like. It means the events are, in a sense, closer in time than they are separated in space. Enough time exists for something moving slower than light to get from one event to the other.
Okay, and negative.
If it's negative, we call it space-like. The spatial separation dominates. You'd need to travel faster than light to cover the space in the time available, which you can't do.
And 0.
0 means the events can only be connected by something moving at the speed of light, like a light signal itself.
Wow. That's a lot packed into those minus signs. The text also mentions setting Ferdinand 1 sometimes. Why simplify it like that?
Ah, yes. That's a very common trick in relativity. It's mostly for conceptual clarity and mathematical tidiness. If you set $2, you're essentially choosing units where time is measured in, say, meters, the distance light travels in a certain time, or distance is measured in seconds.
So you treat time and space on an equal footing, unit-wise.
Exactly. And then the invariant interval squared just becomes $2 by 2 y2 z2. It makes the symmetry really stand out. Time and space are handled almost identically, except for that crucial sign difference.
Okay, this is the part that always kind of twists my brain. How can this strange geometry, this interval with minus signs, possibly define the limits of cause and effect, causality itself?
Right. This takes us straight into section 17-3 and the concept of the light cone, one of the most powerful ideas in relativity.
So picture a space-time diagram. Time going up, space across.
Exactly. Imagine an event, O, happening right here, right now, at the origin of this diagram. Now picture light rays spreading out from that event in all spatial directions.
Okay, like an expanding sphere of light.
But on our space-time diagram, usually drawn with time in one space dimension, those light paths form the edges of a cone. A double cone, actually, one pointing up into the future, one pointing down into the past.
And the sides of this cone represent travel at speed, $30.
Precisely. This light cone is the ultimate boundary marker in space-time. It divides all of space-time relative to event O into 3 distinct regions.
Okay, let's break down those 3 regions. What's inside the top cone?
That's the future of event O. Any event P located inside that upper cone has a time-like interval relative to O. Meaning there is enough time for a signal, or U, traveling at or below the speed of light to get from O to P. So event O can causally influence events in its future light cone.
Makes sense. What about the bottom cone?
That's the past of event O. Symmetrically, any event down there also has a time-like interval relative to O. Signals or objects traveling slower than light could have reached O from those past events.
So these are all the events that could have possibly affected us at event O.
Correct. They are within our causal past.
Which leaves everything else outside the cones.
Exactly. That vast region is called elsewhere, or sometimes the absolute elsewhere, or even the present, though that's a bit misleading. Events out there have a space-like interval relative to O.
Meaning too far away in space for the time available.
Right. To get from O to an event at elsewhere, or vice versa, you would need to travel faster than the speed of light.
Which is impossible.
So events in elsewhere are fundamentally disconnected from O. O cannot affect them, and they cannot affect O. They are outside O's causal reach, and O is outside theirs.
This completely demolishes our everyday idea of now, doesn't it? Like a single slice of time across the universe that's the present for everyone.
It absolutely shatters it. Now is relative. Feynman uses the Alpha Centauri example, right? It's about 4 light years away.
Yeah.
If something happened there, say 3 years ago, from our perspective here on Earth, It's still in our future. We haven't seen the light yet. It hasn't entered our past light cone.
Right. If it happened 5 years ago.
Then it's definitely in our past. We could have received the light by now. It's inside the past cone.
So what defines now for Alpha Centauri relative to us?
Only something happening exactly 4 years ago, whose light is just arriving now, sits on the boundary on our past light cone. That's the closest we get to a shared now across distance, and it's really just the edge of our causal past for that location. Our definition of right now only really makes sense locally, or it depends on knowing things that are strictly within the time-like interval of our past.
That's, yeah, profound. The universe's speed limit basically creates this absolute structure, this cage of possibility around every single event, defining past, future, and this huge unreachable elsewhere.
It's the fundamental framework of reality as we understand it. And while if this geometry dictates where things can be and what can affect what, the next logical step is to ask how it affects how things move. How do energy and momentum fit into this four-dimensional picture?
Ah, so we move from the geometry to the dynamics.
Exactly. And the key concept here is the four-vector. We saw how position coordinates, 6 Dockers, y as z, and time, combine into a sort of four-dimensional position vector, x, y, z.
Okay.
We need to do the same thing for dynamic quantities like momentum and energy. They can't just be three-dimensional things anymore if the underlying space isn't.
So just like time partners with space, energy partners with momentum.
That's the insight. In classical mechanics, you have 3 components of momentum, Tp, Xp, Xp, ZOU. In relativity, these 3 spatial components combine with a 4th time-like component to form the four-momentum vector.
And that 4th component is energy, or related to it.
It's energy, divided by setars actually to get the units right, unless you set Ciani. So the four-momentum vector looks like ECPXPXP EZ day. Energy essentially plays the role of the time component of momentum.
Which means when you change reference frames, when you look at things from a different velocity.
Energy and momentum get mixed up by the Lorentz transformation, just like time and space do. Your measurement of energy depends partly on my measurement of momentum and vice versa.
The relativistic equations for energy momentum, the ones with the square roots involving VTC2 do, they show this.
They absolutely do. You see, energy EEC UNE MSEOC2 and momentum VCZE, where gamma is that factor $1 squared and 1 V2C2. They share that velocity dependence. But the really crucial consequence is for conservation laws.
Right. So hold on. If I'm doing an experiment, say a collision, and I carefully measure momentum before and after, and it looks conserved in my lab, someone flying past me at high speed might look at the same collision and say, wait, your momentum isn't conserved.
They might say your 3 momentum isn't conserved by itself. Because from their moving perspective, some of what you measured as momentum now looks like energy, and some of what you measured as energy looks like momentum. The parts got mixed.
So for a conservation law to be universally true for all observers.
It has to apply to the whole four-dimensional quantity. Conserving just the 3 spatial components of momentum isn't enough in relativity. You must conserve the entire four-momentum vector. The total energy and the total 3 momentum, together as a package deal described by the 4 vector, must be conserved.
That's the absolute conservation law in 4 dimensions.
That's the one that holds true in any inertial frame.
Okay. And just like the space-time interval was the invariant length associated with the position 4 vector, does the 4 momentum have an invariant length too?
It does, and it's incredibly important. If you calculate the squared magnitude of the 4 momentum vector using the same space-time metric, meaning you take the time component squared, energy squared, and subtract the space component squared, momentum squared, times 2c22.
So 2t2, 2c22.
Exactly. That quantity, 2c2 is an invariant. It has the same value for all observers, regardless of their velocity.
And what is that value? Does it represent something physical?
It does. It turns out to be equal to MSE2. That's the rest mass, mLr the particle, squared times C2 to the 4th power.
E22, P2C2 equals M02 C42.
Wow.
Wow. That connects energy, momentum, and rest mass in one fundamental invariant equation.
It really does. It shows that rest mass isn't just some label we stick on a particle. It's this intrinsic invariant property determined by the particle's energy and momentum content, viewed across all possible reference frames. It's the length of the four-momentum vector in spacetime.
And the punchline, the really neat part, comes when you think about light, about photons.
Yes, the photon. We know it has 0 rest mass. $10 equals any dollars.
So if you plug $2 into that invariant equation,
P2C2 equals $2, which immediately rearranges to $2 equals P2C2, or simply we at E taking the positive root.
The energy of a photon is just its momentum times the speed of light.
Directly from the invariant structure of the four momentum, derived from the geometry of spacetime itself. It all ties together beautifully. Dynamics emerges from the geometry.
Okay, let's try to pull this all together then. What does this deep dive into Chapter 17 really tell us? We started questioning simple measurements of space and time, and we ended up having to redefine conservation laws and even the meaning of mass itself.
It's a radical shift. I think we can boil it down to maybe 3 foundational nuggets from this chapter.
Okay, nugget one.
First, space and time are not separate. They are fundamentally mixed by relative velocity, described by the Lorentz transformation. Mathematically, it's like a rotation, but involving time.
Got it. Mixes space and time. Nugget 2.
The one true invariant measure of separation between events in spacetime is the space-time interval. And its definition, T2 by O2y, Y2 Z22, with those crucial minus signs, dictates the non-Euclidean geometry of our universe.
Okay, invariant interval defines a geometry. And third,
causality, what can affect what is rigidly constrained by the light cone. This structure defines absolute regions of past, future, and the inaccessible elsewhere, shattering the idea of a universal now.
past, future, elsewhere.
Yeah.
Defined by light speed.
That's the essence of it.
Feynman often quotes Minkowski, doesn't he? Something about space and time becoming shadows.
He does. The quote is something like, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality.
A union of the two. Space-time.
That's it. And maybe the final thought for you, the listener, is to really consider how deeply this changes things. It's not just tweaking equations. This shift from thinking about independent space and time to a unified space-time fundamentally alters our intuitive grasp of reality, of connection, of cause and effect. It's the very stage on which all of modern physics plays out.